together. Listen up, guys. We are not done just yet. Remember, there is no. We are done in the sense that we are done with the curriculum, but there is that one biochemistry project that is due final. So I'm gonna send you videos. These videos, they are about the biochemistry of the cellular stress and cellular homeostasis. That's very important. You're gonna listen to the videos and summarize them, and I'm gonna send you all the like requirements for the font and the size and all of this. You have more than enough time to listen to them, more than enough time to prepare. I'm not gonna make it. It was supposed to be due like right after the like, for example, today is the final, then next Wednesday it's due, but I'm gonna give you time to like till the final. So please don't think that it's forgotten. It's a big project. It's gonna worth a lot. Make sure that you listen to it and you do well. And it's just listening to the videos and understanding. So it's myself explaining. These are concepts that are very important. Okay. So you can start now. All right, guys. So we're gonna start physics. Physics is the most foundational, most important science of all the sciences. And we talked about physics before in biochemistry. Okay, there's a lot of hybrid. There is a biophysics, okay, and there is geophysics. You heard of geophysics with the GPS? And there's biophysics, the physics of biology, and there's physical chemistry. Physics is the most underlying, most basic of all the sciences. The better you are at physics, the better you will be in comprehending, in understanding, making sense of all the other subjects. Physics will give you the critical skills, the analytical skills to solve worldly, everyday life problems. And you know, the most wonderful thing about physics is that physics is trying to help us make sense of what's happening in the galaxy, what's happening in the world. And the physics that's happening on Earth is happening in the universe. So we use the same laws, the same formulas of physics to install a heating system in your home. We use the same laws to send a rocket out of space. The same physics laws that are used to study the galaxy, the same laws that are used to study the stars, are used to explain phenomena that happened on Earth. Okay? And if I have to define physics, I still remember my first day in high school when I first got to learn about what physics was, and our teacher asked us a very interesting question. What is your brainstorming of what physics is? If just somebody, throws at you, what is physics? People think it's math and complicated problem solving, but in your heart, when you hear physics, what is physics to you? This is not a right or wrong question. If you have to define what physics is, let's see who can come up with the closest definition of what physics really is. There's no right or wrong. This is just trial. Yes, Oxford.
Is it the study of motion?
The study of motion. Actually, that was one of the earliest definitions of what physics is, the study of motion. But it actually became deeper than that. So when we say the study of motion, what do we mean by motion?
How things move.
So yes.
I could be wrong, but I think it's
fine.
like has something to do with like inertia or something like that.
So inertia is the tendency of a mass or a body to retain its state of motion. So if you are in a moving car, so what happens, your body is moving. When they push you and you fall off the car, what's gonna happen? You're gonna start rolling, because initially your initial state was you were moving. But if you are stationary, then if somebody pushes you, you will resist and you will want to be stationary. So inertia is your tendency to retain your initial velocity. So your initial velocity is 0, you're gonna want to be 0. That's why when they push you, you're not gonna move. But once you start moving, if they try to stop you, that's why when the ball is rolling, you want to stop it, it's gonna keep on rolling at you. And if a rock, you want to push it, it's going to try to stay zero. So that is inertia.
Oh wait, okay, my fault. Let me come back. It's it has to do with like energy. So like mechanical energy, chemical energy, kinetic, like.
Excellent. That's the definition. But I want to go to what is inertia. Define inertia.
I don't remember. It's been a long time.
I just said it.
Oh, like basically if a person could stay, like you basically said if a person could stay still or like, yeah.
Okay, that's an understanding. But the concept, you have to define the concept. The concept is inertia is the tendency of a substance or a body to what? That's good. That's business. He's talking business now. That's the tendency of a body to maintain or retain its initial state of motion. That initial state of motion could be zero. That is a state of motion, being at zero velocity. Okay, and what was that you were trying to define what physics is?
Physics is a study of matter, force, and energy.
Matter, force, and energy. Matter, force, and energy. Okay, these are things we study, but force is something bigger. Something is bigger than the initial definition. So when we study physics, we are trying to study time, energy, space, time, energy, space, and matter, and the relationship between them. We want to study the relationship between these four. So force is actually mass multiplied by acceleration squared. So the force equals ma squared. So this is very important because now within this force you have mass. But what is acceleration? Acceleration is velocity divided by the time. Velocity divided by the time. So now the force will equals mass multiplied by velocity divided by the time. So that's why in the formulas they can give you one thing that you have to convert into another. But we are getting to that. We are trying to study, first of all, what is physics in the most basic sense. So now we are trying to understand what is the relationship between time, energy, space, and matter. Okay, we study physics using models. What's a model? What's a model? A model is a physical representation of something we cannot see. You remember the structure of the nucleus? And in the nucleus you have positive protons and you have neutrons that are zero charge, and around them spinning these electrons, like the planets around the sun. Do you really think that's what happens inside that's not, but that's our simple way of understanding. You know, when you tell somebody, you know, how to get to the school, you go like this. You go like that. Is that really how you get to school? But that's a model. That's your way of making a model to make things easier to understand using a representation. That is definitely not 100% true, but it's definitely going to help you have an understanding of where you're trying to get. So a model is a physical representation of a concept you're trying to discover or you're trying to relate. What's a theory and what's a law? We're going to be dealing with theories and we're going to be dealing with laws in physics. What's a theory? What's a law?
An idea.
So a theory, excellent. A theory is an idea. I like that. A theory is an idea. So an idea so for example, idea could be right, it could be wrong. So a theory could be wrong.
Yeah. Yes.
So a theory could be wrong, but it was generated based on some plausible proof that it's right. So there is the Big Bang Theory.
Right.
They didn't come up with that for no reason. There is supportive evidence, but at some point there may be evidence that could nullify it. So a theory is something that is up for grabs, something that could be nullified. And theory is something about multiple things. So it's not clear cut, but a law is very clear cut. Like the law for robbery. I mean, that you commit robbery, you get this. But in theory, you have the theory of natural selection. The theory is more vague. The theory is trying to make sense of maybe more than one thing. But the law is one. So you say the law, that's a law. The force, that's a law, that the speed equals distance divided by time. That's a law. That's clear cut. There is no way around that. So that's a law for speed. We can rearrange that, and we can multiply this side by time and multiply this side by time. Then you get distance equals times speed times the time. So here we learn that sometimes we can define things based on their mathematical formula. That's good enough. If I ask you what time is, you can tell me time equals distance divided by speed. So laws are generalizations. Laws are precise, are clear cut, talking about known things, while theories are more general. And in physics, we are really dividing physics into two different fields. We are dividing physics into two different fields. There is what is known as classical physics. When you say something is classical, what does that mean? When they say that's a classic. That's a classic. What is classic? When you hear the word classic, what do I really mean? Old, exactly. So we don't say old physics, we have classic physics. So physics is divided into two parts. Physics is divided into two parts. Classic physics or classical physics, and then you also have modern physics. So modern physics is divided into relativity and
Theoretical.
quantum mechanics. Quantum mechanics. So what's the difference between relativity and quantum mechanics and classical physics? Classical physics is when you study big things. Remember back in the day when anatomy and physiology was all based on cadaver? They used to call it gross anatomy, is what you see. And then when the microscope came out, they realized that gross anatomy was nothing compared to histology, compared to what you see with the microscope and below. We have in our hierarchy, we have the cell, and many cells give us tissue, and many tissues give us organs. Organs together give us organ systems, and then organ systems give us an organism, and many organisms give us a population. So they thought that we begin anatomy here from the organ, because you can see an organ, you can see the liver, you can see the kidney. But then they realized that this is only 10% of what's happening. They say the tip of the iceberg. The iceberg in water, the part that you see is actually 10%. The 90% is actually under the water. So 90% is under the water. That's why the density of water when it's ice is about 0.9. Is about 0.9. So the density equals mass per volume. So the unit for mass is kilogram per milliliter. So the density for water, while water is liquid, is 1 kilogram per milliliter. But when it's ice, it shrinks. So it becomes 0.9 kilograms per milliliter. And when you put ice in liquid water, it's gonna float based on the density, 0.9 over 1. So that's why you have the tip of the mountain of the iceberg, that's about 10%, or that's about the 0.1, while the 0.9 is actually below. So they saw the same thing, that gross anatomy, the one that we see with our eyes, is nothing compared to the galaxy, the world that's inside. The tissues, the different types of tissues we have. The epithelial tissue, the connective tissue, the nervous tissue, the muscular tissue. Then they saw the cells and what's happening underneath the cell with all these organelles and your mitochondria, your proteasome, and the cytoplasm, and the molecules. Okay, all of these atoms. They saw that from here and below is actually 1,000,000 times more than what's above. So that is known as histology. And this is the stuff that are studying physics at the macro scale. That's classic physics. So studying physics at the classical level is when you study physics when you're dealing with big bodies. Now, relativity and quantum mechanics is when you study with things that you cannot see with your eye. When you're looking at the speed of the electron, the speed of the proton, and this molecule, the fission of the nuclear fission, that is all about quantum mechanics. If you study stuff that are really, really small, that is quantum mechanics. Small, tiny objects. Then what is relativity? So the requirement for physics is that it has to be macroscopic. That's why we study the speed of a missile. You can see the missile, speed of a car, inertia. So it has to be one, macroscopic. Number two, in addition to being macroscopic, it has to be moving at least 1% slower than the speed of sound. So I'm sorry, the speed of light. The speed of light. So the speed of light is how much light travels in meters per second in about a year. So that's a huge number. But you're not responsible of memorizing the number. I just want you to appreciate that these are the two requirements. I'm not gonna study anything moving faster than 1% of the speed of light. That's the job of relativity. If I study something moving so fast, faster than 1% of the speed of light, that's relativity. So here we study slow things that are big. In classical,
That's classic, right? You said classic.
yeah, that's classical physics.
Microscopic.
Yeah, when you study microscopic things that are moving slow. When I say slow, I mean 1% lower than the speed of light, which is really high, which is unbelievably fast. Okay, that's for like star speeds, and that's speed of the galaxy and all of that. But if you want to move faster than that, like how fast an electron is spinning around the nucleus, then you move to relativity. And if you want to study the things that are small, another requirement for classical physics is that there is really weak gravitational attraction. Like Earth. Earth has a weak gravitational attraction of about 9.81 meters squared per second. That's the gravity. That's the gravitational pull of Earth. That's weak. Now compared to the gravity of the sun, now that is too high. That's part of quantum mechanics. So quantum mechanics, we study really small things that are microscopic, really small things that are microscopic, really small things that are microscopic, and they are under really heavy gravitational pull, like the sun, for example. And sometimes we combine both, something known as quantum, when we add them both, relativity and quantum mechanics. We can add them both, and that's known as quantum relativity. So in quantum relativity, you can now guess, what do we study? We study both. We study objects